Hello. I'm going to do a few of the series test problems so then you can see how to do them. The first one, to gain an intuition, I always look at the behavior of, or not the behavior. I look at the sequence that they give me, the equation of the sequence. So in this case, they give us n over n squared plus 5. And this, to me, looks a lot like 1 over n, the harmonic series. And it's important to be able to build this kind of intuition because we know that anything that behaves like a harmonic sequence, or I mean harmonic series, will diverge. And so we are able to use the limit comparison test for this one because I know that I can just say in the beginning that n over n squared plus 5 is approximately 1 over n because the constant terms are almost negligible and we only care about the higher order terms, but the higher order terms cancel out when we neglect this 5. And how do you do the limit comparison? And so if you can get an intuition as to what famous series does this series look like, you could perform the test. So if I'm able to say that the series looks like this, then I'm also able to say that then I can do the limit comparison test. So this is the idea that we want to compare two things to see if the rate at which they increase or decrease are similar. And so what I'm doing is I'm taking the inside of this and I'm basically saying I have a series that's famously known to diverge, which is 1 over n. And I want to take a ratio, so I want to take, if this is a over n, I want to take a over n over b over n and let the harmonic series be b over n. And so if I plug this into the equation, I get n over n squared plus 5 over 1 over n. Just like the keep change flip, you do n over n squared plus 5 times n divided by 1 over n, which is just n over 1. I'm dividing and then multiplying by the reciprocal. And I forgot to include that you should be taking the limit as n goes into infinity for these. Okay, so this is what I have. I'm going to simplify this further. So the limit as n goes to infinity, n squared over n squared plus 5. And this is just approximately equal to 1, right? Because when we take the limit, we compare the higher order terms and we just take the coefficient. So both of these are n squared, so they're moving at the rate the rate in which they're increasing is the same. And so we can cancel these out and then essentially say, I'm going to take the ratio of their coefficients. So the limit is 1. And what does this tell us? The basic idea of limit comparison test is if I know that something diverges, then I know that the ratio, if I compare that famous thing that diverges with something else I know less about, if I can say that the ratio is approximately 1, then I can say that the rate at which they're diverging or converging is the same. I'm saying that the behavior as n goes into infinity is similar. And so that's why any single time for a limit comparison test, if you get a number, if the limit of an over bn is less than infinity, which is just a shorthand of saying it's finite, it's a number, then we can say that it acts the same way, and so an diverges. Okay, now let's do the next one. So this one should be pretty easy as well because this series is almost the same thing as the first one, except for the fact that we have this to the power of n. So whenever you see to the power of the n, you should immediately think to do the root test. So I just want to take, so the root test, basically the main indicator of a root test is if you have up to the power of n. So let an equals to n over n squared plus 5 to the power of n. And basically root test is saying that I want to just take the limit as n goes into infinity of square root of n. This is the root test part of an. Or in this case, n over n squared plus 5 over to the power of n. And you always want to take the absolute value because you can't nth root something negative. And it doesn't really change it if it's negative or positive. Anyways, so I know that these two cancel out. And so what I'm left with is this limit. And when I take this limit, to be more precise, and I know you can probably just guess that it'll go to 0, but to be more precise, what we're actually doing is we're looking at the denominator, the highest degree in the denominator, and dividing all pieces by it. So I notice that n squared is my highest degree, so I'm going to divide the top by n squared. I'm going to divide the bottom by n squared, and also the 5 by n squared. And so long as I'm dividing everything by n squared, it doesn't matter. But look, if you take the limit as n goes into infinity, this actually just becomes 1. This is 0. And this actually just becomes 0 as well. So actually I just get 0. And so what is interesting about this, originally this series, when we looked at it without with the nth root, this one diverged. But the moment you add this to the power of n, we can see that it's enough to tell us that it's enough that the square root of n slows down the rate enough. Speeds up the rate enough so that the value actually gets smaller and smaller, and so it converges. And the main condition of a convergent series using the root test is that the limit must be less than 1. And that's true here. Less than 1, it was 0.